So today I will talk about sums of random variables. So these are the things that I wish to talk about. And then I will talk about some expectation operator. Or integration on omega. There are a few other things one has to discuss, but let us. I realize that I have only 4 more lectures, including today, right? So let's see. Yes. So today is 25th. Then I have one lecture on 27th. Then on 2nd and 4th. Yeah, so I have only about 4 lectures. I should be fast. And then the main thing that remains is the central limit theorem. Let me write out what I remains to be done. Central limit theorem. And that will require for me to discuss characteristic functions. Okay, these are the things that I need to discuss about, and then some properties. So here itself, based on integration on omega, some properties and characteristic functions and their properties. Their properties. Okay. Besides also doing some examples. So let's get started off. So these sums of random variables, this is sort of part of a general discussion which is already over, but just to emphasize, so suppose that x and y are random variables, okay, continuous random variables with joint density functions, density function fxy, okay, x comma y. So we need an expression for, we need to find density of x plus y. Okay, so we have done some problems actually involving such things, maybe more complicated things. Okay, so you just let me explain how to do that. So you just set u is equal to x, put u is equal to x, and v is equal to x plus y, and then you know how to find the joint density function, joint density function fu comma v, or u comma v. Okay, and then once you have this, then we obtain yeah, this is it. So there's nothing So we obtain f of x plus y, which is of course f of v. Okay, this is equal to, well, integral minus infinity to infinity fu comma v of, yeah, so u comma v du. That's it. So, but then how to compute FUV in terms of UV? Well, I mean, yeah, you can do that. So, or you can do it also directly just by computing the. So let me do it in a different way. So okay, the thing that so we have already done this several times before. So x plus y. So x comma y. So you need to write down the Jacobian. Let me just skip a few things. So Jacobian of x comma y with respect to, so you have to write x is equal to u, no problem, and y is equal to v minus x, but x is u, so v minus u. And now you compute that for the Jacobian, you can just compute the Jacobian matrix and the terms will be equal to actually the function 1, constant function 1. So du dx dy is of course du dv. And now you just, all that remains is to compute that for fu comma v, fu, sorry, capital U comma v, or u comma v is just you substitute in here fxy. Uh, so fx comma y, x is equal to u, and y is equal to v minus u. That's it. Okay. So in particular, yeah, I mean, so you can write a probability of x plus y, that is your this thing less than or equal to v, is integral minus infinity to plus infinity of uh, f of u comma v minus u. So mind you, v is a constant here. V is rather fixed. Okay, du. That's it. And the thing is, if yeah, so if um, x comma y are independent, then so you know that f of x comma y of x comma y is equal to product fx of x, fy of y. Therefore, so you may write f of u comma v. Yeah. Well, you can also say that in that case, f of yeah, in that case, x comma x plus y are also independent, and directly also, therefore, you can say this. So, uh, mhm, mhm. Just one second, I want to say something. Yeah. So, mm, okay, so may write here. I think I realize I made a slight mistake here. This, of course, I have to integrate it with respect to this, but this is the distribution function. So minus infinity to v of here. Okay, so let us just change the variable here to z and then write something else. Or you can write t, doesn't matter, dt. I realize I missed that. Okay, because here you see x plus y less than or equal to v. You are right. This density we have already found out. Okay. So yeah, so therefore what I wanted to say was f of x plus y of uh, z, no? F of, okay, let's just write z. This is equal to integral. So integrate it with respect to u here. Okay, minus infinity to infinity f of, so if u comma v, u comma z minus u du, but this is same thing as, this is same thing as integral minus infinity to infinity fx of u and fy of z minus u du. And this has a name, that's why we want to discuss this. This is an important operation. Yeah, let me just write this. This is an important operation called convolution product. This is yeah, this is what it is. Okay, so of z. So typically when you have two functions, uh, yeah, so here for two, well, integrable functions f and g, for us they are all okay. I mean density function, so integrable. So f star g define the convolution function uh, f star g of z to be integral minus infinity to integrable functions on real numbers. Maybe some uh, yeah, from further hypothesis, I'm not sure it's required. Yeah, f of, this is f of x or f of u, g of z minus u du. And this is also same thing as integral minus infinity infinity. You can put change the variable. Okay, z, this is equal to z minus u, z minus v. Let us write it like this: g of v dv. Both are the same. This is just by substituting g minus u equals v and then write everything in terms of v, and there yeah, there will be a change in the sign, but that is compensated because you write minus infinity to infinity. Okay, so when you do that you get this, but this is same thing as g star f of z. So this is convolution product. So here some, well, I mean I never defined what this is. Okay, so let us, yeah. Okay, so this is what. So the convolution product is commutative and it's also associative. Also, f star g star h is also equal to f star g star h. Well, this is not surprising because at the moment, suppose you believe that f, g, h are all density functions. So if f, g, h are densities, then uh, both sides are uh, the density of x plus y plus z, assuming that at x, y, z are independent random variables. Okay, so all right, so this is an important operation. Let us just do an example. Uh, yeah, I have. Okay, let us take x and y is actually given in the book as an exercise. Let's just do this. Yeah. Maybe find the density of x plus y, where fx of fx comma y of x comma y is equal to 1 by 2 x plus y exponential minus of x plus y. Okay. So put x is equal to mu, y is equal. Although we can an algorithm and so on, it's better to do these things separately. So what you want, we just call that v is equal to x plus y, so that yeah, so y is equal to v minus u, and Jacobian of course is 1. Yeah, therefore, so dx dy is absolute value Jacobian times du dv, so du dv, and f x comma y of x comma y is equal to, substitute here. So I write simply f of uh, u comma v minus u. But when you do that, this is just my f comma y. Okay. So when you do that, what do you get? So everything is a function of x plus y. So from there itself, you can directly see that this is half of x plus y, half of v e power minus half of. So this is is also, yeah. So if you write here minus v, okay, and so f of uv. So the So I write always like this: x y x comma y dx dy is equal to f u v u comma v dx dy du dv du dv. Okay, so this is just therefore. So here we just now calculated this. Therefore, or here you can write since. So, so what do we have? FUV u comma v is equal to 1 by 2 v. There's one small thing to explain is minus v. What is to explain here? So here, okay, I forgot to state this. X comma y bigger than or equal to 0. Okay. Now here, now you have to worry slightly. Okay. What are the ranges for u and v? U is same as x, so no problem. U is bigger than or equal to 0. That's no problem. V is equal to x plus y. So y is greater than or equal to 0. So that means that v is bigger than or equal to u. This is important. We just cannot forget the domain also. Okay. So the difference between f and this thing is that here the domain is not just simply v bigger than or equal to 0. V is bigger than or equal to u. How do you get that? Because y is bigger than or equal to 0. That means v minus u is bigger than or equal to 0, which means the same thing as v is bigger than or equal to u. So this is the thing. So or equivalently, you can write 0 less than or equal to u, and this is less than or equal to v. And of course, v can go up to infinity, no problem. This is it. Okay. So this is the density of x plus y, which is v. No, sorry. So what have we found? We have found the uh, joint distribution. So what is the problem? The problem is find the density of find. So here it is. Find the density of x plus y. Okay. Find the density of x plus y. This is a joint density function. Therefore, the density we need to write fv of v. Fv of v is equal to integral. You see, although it involves only v here, it doesn't mean that this is u and v are independent. That's because the range of v depends on u. So this is something that you should know. I mean, you should pay attention to. So write the general formula minus infinity to infinity, but what matters, so you always write the general, I always do this, uv, uv, du, but this is perfectly okay to write it. The convention is that outside of this range, the function is 0. So it becomes 0 to v. Okay. And then here, 1 half v e power minus v. Okay. And the integration is with respect to u. Okay. So how does this work out? This is equal to 1 half v e power minus v times the length of this interval, which is v, and therefore this becomes v square. Okay. So this is the thing. Okay. And of course here, see, having integrated with respect to u, now this is something that is depending only on v, and v can be greater than or equal to 0. I hope I did not make any mistake here. Yeah, I can just check that this is a density function. Okay, let us move further ahead. Uh, I'm wondering if I should do one more problem. Yeah, why not? Let us do one more problem. Okay. So take example. Uh, X is equal to normal variate sigma 1 square. Y is equal to normal variate this sigma 2 square. You can do more general thing with mu1 and mu2 here, but let us just stick to this and are independent. Independent. Find the uh, density function of x plus y. So yeah, okay. So let us do this. So fxy, fx comma y of x comma y. Well, this is equal to, so 1 by root of 2 pi sigma 1 e power minus x square by 2 sigma 2 times sigma square. So here again 1 by root of 2 pi sigma 2 e power minus x square y square by 2 sigma square. So that's equal to, so 1 by 2 pi sigma 1 sigma 2 and then e power minus of x square by sigma square, so little x by sigma square plus y square by sigma 1 square by sigma 2 square divided by 2. Okay, this divided by 2 is in the exponent. So okay, so now this time I suppose okay, so this time we just apply uh, directly the, because it's independent, I want to use the convolution product. So f of x plus y of z is equal to integral minus infinity infinity fu. Yeah, I'm going to write the same thing here. Sorry. uh, uh, so this 1 by 2 pi sigma 1 sigma 2 I will write outside. It's going to appear here again anyway. One by 2 pi sigma 1 sigma 2 integral minus infinity infinity fx of u, which is e power minus of u square by sigma 1 square times e power. So if you forgot the formula, I just show that formula for you once again. This is the situation when this is, yeah. So f of u, fx of u, fy of z minus u. So, okay. So now you write here minus of z minus u, z minus u whole square by Here there's a 2, here there's a 2 sigma square, sigma 2 square. Okay, du. And I don't think I will complete this, but just do a little bit more of simplification. So minus infinity, infinity, e power minus u square by 2 sigma square. And here, so you expand this, e power minus of, so you will get u square minus, no, plus. Okay, let's just write the product term. 2 u sigma u uz and then plus z square, whole thing divided by 2 sigma square, sigma 2 square, and du. Mind you, whatever you get must be a function of z, otherwise you are wrong. You made mistake somewhere or the other. 1 by 2 pi sigma 1 sigma 2 integral minus infinity infinity e power. Now this time you simplify, put the u terms together, minus u square by 2. So okay, so we need to write it in this particular fashion. I just write u square and then 1 by 2 sigma square, sigma 1 square plus 1 by 2 times sigma 2 square. Okay, I get that out of this one. And then you write e power minus 2u sigma 2uz divided by sigma 2 sigma square, sigma 2 square minus z square by 2 sigma square. Okay, so at this stage I stop, and it turns out that after you do some simplification, so after simplification, so it turns out it should be turn out that z equals n now 0 sigma 1 square plus sigma 2 square. Okay, that's what it should be. Yeah. So I'll take much longer time than is necessary to do this, and I don't have the luxury of time. I leave it as an exercise for you to complete this. Okay. Yeah. So okay. So next thing that I want to discuss is let's just go back. What is the plan? Expectation operator. We need this discussion because the proof of central limit theorem will require some theorems to quote from some abstract analysis, which is why I go into this discussion. Okay, so recall now, let omega f p be a probability space and x from omega to real number a random variable okay. Thus f is no, not f, x is f measurable. We used this long time back, is f measurable. this is simply equivalent to the statement that if I just think of x as a function and look at the inverse image of minus infinity to any point a, now this is an element of f. That's what it means to say a random variable. Not just some arbitrary function, but it is a function with a property that when you just look at pull back of this, maybe with a included, doesn't matter really. In fact, open sets, that's the main thing. So that is in here. Okay. The moment this is there, then I can take any Borel measurable set in the real numbers and look at that, and that will be in F again. And we may as well assume that F is complete and so on. Okay. So the thing is, we may think of, so we think of omega F, uh, yeah. So P as a measured space. This is the main thing, is as a measured space. Measure space. What do we mean by that? So that is, if if A is in omega, we want to be able to think of, associate meaning to the statement length of A or area of A, whatever, or volume of A, depending on whatever. But okay, if omega is an interval or an open subset of R2 or an open subset of R3, in these cases we'll say length, area, whatever. But omega is an abstract space, okay, set, and F is some collection of subsets, and P is some association involving something. But that's exactly what you want. That is, if you think we associate. So measure of A must be a real number. In fact, for our purposes, it will be a non-negative real number. So you can think of it as content or volume or whatever. So imagine that omega is a subspace of R3, and then you are able to associate something like a volume. And volume of whole of omega itself is 1. Okay. So that it is normalized in such a manner. In fact, you will see that in a minute. Associate its measure it as probability of A. Sorry, I wrote omega here. So A is a subset. So it should be in F. You don't associate measure to arbitrary subsets, only sets which are, well, F measurable. So such sets which are in script F. So this is a number between 0 and 1. Okay. Notice that measure of the whole space is 1, and measure of the empty space, of course, is 0. And the usual thing, if A and B are disjoint sets, measure of A union B is measure of A plus measure of B. We just don't call it measure, we call it probability. Okay, so probability is the same thing as giving you measure. And now notice that. So, okay. So what we want to do is, like in real numbers system, when you have, okay, so like I said, the problem is that if you have in R or R2 or R3, we have notion of, or whatever, we have a notion of integration. Okay, and we want to be able to do similar type of thing on omega, and that's the main thing we want to do. Okay, how do we do that? So we want to mimic what was the basic thing. In fact, you will study this in greater detail in your real analysis course. At the moment, what we are doing is abstract analysis. So much more than just doing analysis on R2, R3, but it is abstract analysis in the sense that omega is some abstract set, F is some collection of subsets satisfying some axioms, P is some probability, whatever, satisfying those axioms. Okay. So what do we do? First of all, while defining the notion of integration, you do it for what are called simple functions or elementary functions. So, mm, elementary function. So, so, so we want to, uh, as I said, our goal is we want to integrate random variables, random variables x. Okay. So first do this. First we do this for very special type of random variable, which are indicator functions. Maybe I wrote I sub a in f. Okay. In this case, this is just in this case, well, you want it to be measure of a. Okay, integral x over omega. So the notation is dp. This is nothing but we want it to be p of a. Okay. So this integration notation is integral over omega dash dp. So you extend it linearly. If your function x is a1 ia1 plus blah 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 plus an ian. Never mind if a1 a2 they are disjoint or whatever it is, doesn't really matter. If this is, then define. So in other words, you define this integration operation linearly as a real linear operator. Okay, integral x omega dp to be, well, so you see, this is, as I said, you must think of this integration as length of a. Okay, so a1 times length of a1 times p of a1 blah blah blah, an times p of an, and this is nothing but summation ai integral over omega. Okay, so indicator function iai dp. And I want to say that in the case of indicator function, random indicator random variable, this is also equal to expectation of IA. And so when you write it like this, okay, now this means that I have a discrete random variable, and then this turns out to be equal to just expectation summation ai expectation of iai, which is exactly the expectation of x, nothing else. So in this case, it is just this. Now suppose that, now you pass to the limit. Suppose that x1 blah 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 xn or random variables. Yeah, okay, let me say it in this fashion before I say this something. Suppose that x is any random variable. It can be approximated. Well, uniformly uniformly by. So these are called, let me give it a name here, simple random variables. Definition. Simple. So simple random variable is one which is a linear combination of these indicator functions of events approximated by simple random variables. Now define. Okay, so there is a slight thing here. So first you have to define it for x bigger than or equal to 0. Define for x a non-negative random variable. There is a problem, I tell you why. Negative, non-negative random variable or a non-negative random variable integral over x. So simple random variables, let us just call this xn's. So xn's. Okay. So here integration is over omega x with respect to the probability measure dp. This is limit n going to infinity. Okay. Integral over omega this xn dp. Okay, so what is this? Of course, this you can rewrite this in terms of limit n going to infinity, expectation of xn. Okay, now the thing is, yeah, this limit may not exist finitely, it could be infinite. And if when it is infinite, this is also infinite. So this is also equal to expectation of x. The thing is, it may not exist finitely, it could become infinite. If it is infinite, you just say plus equal to plus infinity, that's it. And how do you extend this definition? So you may say that x is integrable if this is finite. Okay, you can use that language. X is integrable if expectation. So first of all, you define it only for positive, non-negative. So x bigger than or equal to 0 is integrable if Ex is finite. For a more general one, if x is arbitrary, it can assume positive or negative both. Okay, arbitrary random variable. Then what you do is you write x is equal to difference of two random variables, both of which are non-negative. X plus minus x minus. This is a trick where x plus is equal to maximum of x comma 0. So you think of some kind of a graph of x. So whatever is above the x-axis, you are taking it to be 0. X and x minus, you take it to be minimum of x comma 0. And so it will be negative when x is negative. So in order to make x minus a positive thing, you just put minus in here. So now x minus is also non-negative random variable. So x is the difference of two random variables. And now define just extension, that's it. Define okay, so yeah, first of all, expectation. This is same as the usual old expectation, no different. So this is equal to expectation of x plus minus expectation of x minus. So this side is also integration over omega of x dp. Okay, so this is equal to yeah, let me write that. Okay, so provided uh, at least one of them is finite. So you can make sense of this, at least one of one of if x plus, you have x minus is finite. Okay, so if both are infinite, in this case we say x is integrable, x is integrable. If this is finite, which means that both must exist and are finite. If x plus and x minus are integrable, that we have already defined. And an immediate exercise is that x is exercise. Well, it's actually trivial. X is integrable but only if mod x is integrable.
Sir,
Yes.
sir, I didn't get why did we need to break it in non-negative parts?
Why did I want what? Non-negative part. Okay, otherwise
Non.
this limit may not exist. No. So you see, you may have a so here. Suppose each when you have a finite sum, there is absolutely no problem. I equals 1 to n. Let me emphasize that I equal to 1 to n. Now when I have arbitrary signs and I just add up all those things, um, see,
Okay,
I
okay,
don't
I
put
think
any
I get
restriction
it
on
now.
A1, A2. They can be, you know, uh, yeah. So it may be wildly oscillating between plus infinity. I mean, it can become unbounded in both directions.
Oh,
Then
okay,
I
sir.
have no way to make sense of it. So basically, we can only add positive quantities. Negative quantities we can manage so long as it's within. Yeah, so that's the basic idea. Okay, you understand?
Yes, sir.
So also there will be no problems with the rearrangement. I was very vague in saying, okay, you just choose any. I mean, all these things require a lot of proving. So mm, I'm I'm just condensing quite a lot of material in just one half of a lecture. So one has to do these things rather in a leisurely pace. Of course, all this will be done in your analysis course. Definitely in analysis 3, but maybe earlier than that. I don't know. Okay. When you study Riemann-Lebesgue, Riemann-Stieltje integral, I don't know if you have already studied that. Already some problems arising in this context will have been dealt with in some detail. And when you study Lebesgue measure, there you will see the full force of it in the special case of real. But I should again say, real integration over R is not a special case because R is unbounded. Yeah. Whereas we are looking at probability measure, where the whole space has measure equal to 1. Okay. So that's the difference. Yeah. So we are in a slightly more general situation so far as omega is concerned, but somewhat restrictive in some sense, in the sense that we are looking at this measure where the whole space has measure equal to 1. Okay. So this is the notion of this, but some convergence theorems are absolutely essential for us, and I will state that. Okay. So there are properties. So this is a monotone convergence theorem. monotone convergence theorem. So we'll assume that xn omega bigger than or equal to 0 for all omega, and xn omega less than or equal to xn plus 1 omega for all n, and for all omega. Okay, then so hereafter we will write expectation. By the way, one has to check that this. So this. So this is of course obvious if you have a discrete random variable. Okay, in this case, um, with the finite expectation. Okay, so that this expectation is same as the old expectation, and then we said that okay, we pass to the limit and so on and so forth, and finally I said that this is exactly equal to expectation. It requires some proof, at least in the case of continuous random variables, this requires some proof. Okay, not too much, but some further discussion. So this equality is with respect to the old definition of expectation. So in other words, what I am saying is, if x is a continuous random variable with finite expectation, whatever we have defined here, so this is okay, um, coinciding with the old thing that we have defined. Okay, so that's something that I have to say that. Uh, okay, all right. Then we can I can rewrite everything just in terms of expectation instead of each time writing this notation, abstract integration of x dp over omega. So, or let me write this. I wish I had a little more time, but so I started off with this one a little too soon. Maybe I squeeze that here. Okay. So when remark, if x is a continuous random variable, then integral over omega x dp is equal to integral x fx of x dx between minus infinity and infinity. Okay, where fx of course is a density. So this is an important remark, and because of this, hereafter we'll just simply write ex for the entire thing. Okay. So you see, how do you prove this? This again is because fx can be uniformly approximated by uh, uniformly approximated by uh, uh, simple functions. Here again, just because I have defined it doesn't mean it exists. Always remember Cauchy distribution if it is finite. Okay, but if it is infinite, then this side is also infinite, it will not exist. So when both sides, this makes sense and is valid precisely if either one of the two sides is finite. Then assertion is that the other side is also finite and it exists, and these two values are equal. So it's a long sentence. I have just rolled it into a very cryptic statement. Yeah. So there is no substitution for reading the textbook. They write a voluminous thing, and then it's impossible to have an entire discussion and written up in a lecture like this. Okay, let us start with this one. Then it makes sense. Then limit n going to infinity e of xn is equal to E of x, where what is x? X of omega is by definition limit n going to infinity xn of omega, where x is the random variable defined as, okay, x omega is this one. So this is indeed a random variable. All those things one has to, in the sense that, so the statement is that if each xn um, is a random variable, or f measurable. So if each xn is f measurable, x is also f measurable. So x is a random variable, and if each xn satisfies this property for all n and for all this thing, so this monotone comes from here. So it's pointwise limit. It exists well finitely. Okay, so yeah, so if it doesn't exist, then there's a problem, because it could so happen that all these go to infinity, and then this may not exist finitely, and so we'll assume that it exists finitely. Okay, so you will see that when you study measure theory, the right thing to do is not work with R, but R union infinity. Anyway, so you can just think that x is actually the limit of all these things. So assuming the limit exists, so limit exists finitely. Okay, exists finitely for all, but yeah, except for a null set, except for omega in a null set. Null set means set of measure 0. Okay. Of course, it could so happen that this side is infinity, in which case this side also is infinity. But the important thing is, if this side is finite, then this side is expectation of x is also finite. Okay. And now there is another theorem, dominated convergence theorem. Dominated convergence theorem. So you will study this monotone convergence theorem, dominated convergence theorem in analysis course. Maybe analysis 4, I don't know. You don't study that in analysis 3. I know that for a fact, because I taught analysis 3 some time ago. Okay, so what is this theorem? So if suppose that I write this very briefly, suppose mod x and omega is less than or equal to mod y omega for all omega, and expectation of absolute value of y is finite. Okay, then yeah, limit then let me write this briefly. Expectation of xn, which is same thing as integral over omega of dp, so of xn goes to e of x as n goes to infinity. Okay. uh, yeah, sorry, there is no, I don't think there is anything here. Yeah, yeah. Okay, so yeah, this is what I wanted to say for today about this one. I can talk about uh, uh, maybe the next topic to this is all I wanted to say about abstract integration on omega. So, what is the other thing I wanted to say today? Uh, I don't want to state central limit theorem, but the next thing to study is characteristic functions and their properties. Since time is short, maybe I continue with that. Okay. So I want to talk about characteristic functions. Characteristic functions of random variables. So as a prelude to that, um, recall that uh, yeah, so the mth moment of a random variable x is defined as so so expectation of x power m, which is integral over minus infinity infinity x power m fx of x dx. Okay. Now it's sometimes convenient to think of x power m by m factorial and then introduce a variable t. Okay. T power m, and now t is just a symbol. You can think of t also as a variable. There is nothing wrong in thinking of t as a variable, in the sense that t is a real number. You can think of it that way, or you can think of it formally. And then what is you can ask, okay, what is this? You can ask, what is this? This is equal to, of course, nothing has changed. Integral this to this, and then x power m t power m by m factorial fx of x dx. And now what you do is add everything. Okay, m going from 0 to infinity, x power m by m factorial t power m. E of that, well, this is the same thing as, okay, you can pull out E out of this sum. Everything you can think of as formal thing. First of all, this may not exist, so we have to assume it is finite and so on and so forth. Then you have this, okay. Uh, this is a summation over x power xt power m by m factorial, okay. M going from 0 to infinity of this is same thing as integral minus infinity to infinity. You put all these sum inside here, you will get e power xt f fx of x dx. And of course, this is no surprise because this is just same thing as e of e power xt. Okay. So you could have directly written it this way. But the thing is, this may, again, let me emphasize, just because you have defined something, this may or may not exist. Okay. However, so this is what is called, in fact, moment generating function. There is a chapter or section devoted to generating functions. In fact, a whole chapter devoted to generating function. I want only a small part of it. So this is generating function. generating function for moments. You can have generating function for many other things. Okay. Now, see, the problem is, yeah, I just now define phi of. So you see, you can just think of this as a formal variable t. So phi of t, phi x of t as, so as integral minus infinity infinity. You just put here e power I x t. That's all you do, and fx of t, d, fx of x rather, dx. And the thing is, this always exists. This exists always. Why so? Because, okay, you take the absolute value of the integral that is dominated by the absolute value of the integrand. Anyway, this is a density function, so non-negative valued function. But this one, in fact, it takes values between 0 and, sorry, so wait a second. So whatever it is, this is taking values in the real number. Let us, yeah, I suppose this may still have some. Um, yeah, this is a density function. So we are dealing with a continuous random variable, and this is density function. So let me say emphasize that x is f x is continuous random variable. If it is a discrete random variable, we have to do it separately in a different manner. The most obvious thing, but this is density function. So yeah, it takes only non-negative values. When I take absolute value, this becomes, so because integral, you write the summation here, minus infinity infinity. This is my last remark for today, and then I'll fx of x dt less than or equal to integral minus infinity infinity. You can take the absolute value inside, then this becomes 1. Ixt, x and t are real variables, and mod fx, I don't need to worry about that. I can just write x dx, which is in fact, so this is 1, and this whole integration gives me 1 because f is a density, since f is a density. Okay, so that makes this always, see, without the I, it may or may not exist, and all kinds of convergence problems, etc. The moment you put I there, it always exists. And this is a nice property to have, and we call this phi x of t is called the characteristic function. Characteristic function of the random variable x. When x is discrete, yeah, let me say that if x is discrete, we define it as, we define phi x of t as. Actually, having described this more abstract situation, I don't need to single out these things, but I do define it as summation e power I x and t f of x and x. So here, okay, I can ignore this x. I don't need to write n. Anyway, it is 0 if x is not in the range. So I just write it like this. Okay. All right. So we stop here for today. In the next lecture, we will study properties of this. Yeah, that's all for today. But I ask you to work out some problems. I keep saying that. I have worked out some problems for you because I didn't have enough time to discuss them in the lecture. I will upload them tonight. Okay, that's all for today.
Sir,
Uh,
uh, so
yes,
since you mentioned it, like, is there a lot of difference between bounded and unbounded measures?
there will be a huge difference. Yes, yeah,
Oh,
yeah, yeah. So
thank you,
you
sir.
see, for example, if f is f, if absolute value of f is bounded, you can always integrate it over omega. But I cannot even integrate the constant function 1 over the real numbers. Okay, doesn't exist. So yeah,
Okay.
unbounded measures, you have to deal with them very no, see, the main thing is you cannot integrate polynomial functions and so on a space on real numbers, correct? You can
Yes.
integrate it on compact intervals, but never mind, you can still develop theory of integrable functions and so on. uh, it's a very vast theory, rich theory. You will study it quite a lot when in your MSc program. A whole lot of functional analysis, LP spaces, Hilbert space, etc. When you are so again, the, I mean, it's not like the theory is divided into two disjoint parts or something. You just study theory of integration over a measure space. Okay, so that's what you will study. Okay,
Okay, sir.
so the so what the difference will be, what type of functions can be integrated. Okay, so when you are confining your attention to only the unit interval, well, any continuous function can be integrated and so on, but you can't do the same thing over real numbers. Let me stop sharing. If there is any more question, I can answer that one or two quick question. Otherwise, we stop for now. I'll continue in the next lecture. Okay, stop for today.
Thank you, sir.
Yeah.
Thank you, sir.